Let's see. Oh, whoops. Share screen. So, some of you may already know the solution to the first one, but we'll just go over it anyways. So let's just let you read through it a bit. Okay, so we'll look at number 1. So, okay, so do two of you want to play number 1? If let's say you don't know how to solve it just yet. Yeah, so one thing we might do to start exploring, if let's say we have no prior knowledge of this game, is well, let's say we have just one stick, right? So if we have one stick, then it's losing, right? Because we do not want to take the last one, so 1 is losing. If there's 2, then it's winning, right? If the current stack is 2, I can win by taking 1 away and then leave my opponent with a losing position of just 1 stick. If it's 3, it's winning because I can just take away 2, right? And then, what about 4? Well, no matter where I go from 4, I'll always give the opponent a winning position, right? So 4 is losing because all moves lead to a winning position for my opponent. So maybe we should define what the terms are, right? So losing position, any possible moves results in a like winning position for the opponent. So opponent can win with perfect play. Right. So then we can continue this. If I have 5, now I can just take away 1 and give my opponent a losing position, and then they'll be forced to lose because I can play perfectly. And then 6, oh, it's winning because I can make my opponent losing. 7, oh, all moves make it go to a winning position for the opponent. So yeah, what's the pattern here? Yeah, so everything that's 1 mod 3 loses. So let's see. Yeah, so what should the player 1 do to win if there's 26 sticks? And let's see, take 1 away. Yeah, I think that's right. Right. So if I have 26 stick, that's 2 mod 3. So if I take 1 away, it'll be 25, and that's losing. So then no matter what, uh, so let's continue. If I give my opponent 25, no matter, what if my opponent takes away 2? What do I do? So yeah, so if opponent has a losing position and they take away 2, then I take away 1 and I leave them with another losing position. If they take away 1, then I take away 2, and that leaves them with a losing position again. And it says the person who takes the last one loses. So, we can force the opponent down to 1 mod 3 or just 1, right? Okay, so that answers B as well. So yeah, maybe we can look at number 2. So what changes if it's not just 1 and 2, it's 1, 2, or 3. Maybe we can uh, explore this the same way where we try small cases. So 1 was losing because you don't want to take away the last stick, is the rule of the game. Let's see, 2, I can force the opponent to 1. I can force the opponent to 1. I can force the opponent to start their turn with 1. Yeah, right. So it's 1 mod 4. Is losing. So 5, all moves go to a winning position for the opponent, or all moves leaves the opponent with a winning position. So yeah. And then here we can, force this, force that, force that. So it's the same thing. Yeah. So we can solve all of these in the same way. So there's 2 versions of this. One is where you do want to take the last stick, and one is where you don't want to take the last stick. And if you do want to take the last stick, then it's just shifted by 1. Like if you do want to take the last stick, and you can take 1 or 2, it'd be like winning, winning, losing, and winning, winning, losing. And then, yeah, everything 0 mod 3 would work if it's 1 or 2 sticks, if you do want to take the last stack of sticks. Oh, whoops, this is winning, losing. Yeah. So here, everything that's 0 mod 3. So, do want to take last stick. Okay. And this is with 1 or 2 sticks each turn. So, okay. So then let's try number 3. So how can we investigate this, I guess? Uh, so maybe we'll do the same thing. Let's have 2 stacks. One is for sticks, one is for stones. Let's say we have just 1, right? So this is losing. If I have this is also losing. Now let's say the sum of them is 2. So is this, let's see. For stones, I think second player wins. And you guys can just say it out loud too. There's only 4 of you today, so wait. Well, so the last object is whoever takes the last object loses. So if it's currently your turn, and losing means for the current person's turn. So let's try 2, 2, and 2. So let's see. Here I can just take away 1 and leave my opponent with a winning. I can take away 1, leave my opponent with a losing, I mean. Here I can take away 1, so these are winning, right? I can force my opponent into a losing position. So what about 3? And we don't have to investigate half of these because, yeah, by symmetry, it's fine. So we can take away 2 and make the opponent losing. We can take away 2 and make the opponent losing by taking away 2 from there to go to there. We can take, and then these are the same. So it looks like with 3 total objects, you can force the opponent to a losing position. And then, so the first player just wins. Okay, what about if there's 4? For 3, player 2 wins? No, I think player 1 still wins. If N1 is losing, then I'm not sure if that's always true. So let's see. Let's just look for more evidence before we try to conjecture. So what about with 4? So no matter if we take away 1 or 2, we'll go into one of the winning positions, right? So these are all losing. Yeah. So we don't need to go down more. Okay. So then what about with 5? Is that winning always? Or is it just winning sometimes? Let's see. So, okay, well, with 5, I can just make it go to a losing from here. So this is winning. Go to a losing from here. And then 3, 2 can go to 3, 1. So that's winning. If I try 6, 0, 5, 1, 4, 2, this I can just take away 2 from the bigger stack, and it'll be winning. Let's just double check, with 7. So regardless of whether way I take away 1 or 2, I'll be in one of the winning positions, right, for the total. So we can only take 1 or 2 from the same stack. Okay. So yeah, it looks like it's like the same as before, right? So well, so 1, if the sum of the number of objects is 1, 4, 7, or 10, then it looks like we're losing, right? Otherwise, it looks like we're winning. So yeah. And this seems to always work. Like regardless of how the 7 are split between the 2 piles, you'll always be losing. Regardless of how the 8 are split between the 2 piles, you'll always be winning. But as long as you leave the total number of objects, sticks, or stones to be 1 mod 3, you force the other player to lose. So yeah. So yeah, proof you would just induct, yeah. So you could say that there's three base cases. Like you could just do the base case of 1, 2, and 3, and then say for case, if it's true for case x, then x plus 3 is the same state. Like it's the same state of winning or losing. So you can definitely write a proof for it, and maybe yeah, maybe there is a so all of these this is what you could call invariance. So when a quantity changes, it varies. If it doesn't change, it's called an invariant. So you can just read through this. Yeah, so this was like the first problem we did. So there's also invariance and other things in science. Um, so at some point, I think it defines what a losing and a winning position is. So a losing position, I'll just highlight it. Is this the highlighter? No. I'll extract text. Well, I don't know if you can see my mouse, but yeah, it says a losing position is a position in a game where a player cannot win, assuming that their opponent plays perfectly from then on out. And then the winning position is just like you can force the opponent into a losing position, basically. Uh, yeah. So yeah. Okay. So I guess we can yeah. So 3 seems good. So here we have 29 total objects. So I guess what is that? It's not. Is it? It's not 1 mod 3. So it's winning. Yeah. Okay. So 3 is solved. I think 4 is really hard. Let's try 4. I don't remember it quite exactly. So I think it's good to work backwards. So what does it look like? Uh, the stacks, have to be. So I'm just working backwards from like the final state of all 3s to like undoing each step, like combining them. Yeah, so Alan says it looks like 3 mod 4, right? Like all of these are 3 mod 4. So is that always the case? Like let's say I have something of the form 3k plus 4k plus 3 and 4j plus 3, and I combine them. So how much will the total, so if I combine them, how much will it be? Let's see. Well, we'll have 4j plus k plus 6, but then we have to add one more, right? Because each move is like you remove one stone and then you split it. So to undo that, you combine two piles and you add an extra stone. So yeah, so we'll have 4j plus k plus 7. So yeah, this is definitely 3 mod 4, right? So if I start off with two things that are 3 mod 4, I'll always, the resulting combined pile will also be 3 mod 4. So then is it possible for us to start with this number and go to all threes? Yeah, this is 1 mod 4, so it won't work. Right, it won't work. I think I actually didn't see how to do this very quickly last time, so it's good that I solved it quickly this time. Okay, so instead of nim, we have dim in 5. See what dim is. Yeah, I guess everyone here is dim because the paper says it's a game of dim. Okay, the game of dim, we have several heaps of stones. They remove a number of stones from any pile that is a divisor. Okay. Okay, so let's just ignore the last sentence for now. It's okay. Once we solve the problem, we'll be less dim. We'll go on to the next problem, which does not mention dim. So solving the problem will make us all slightly less dim. Okay, so let's just say, I think, hang on. Is this really, okay, it's fine. So this is like, I think a better name for this would be proper factor or something. Okay, so we want to take the last stone. So when is take the last, oh wait, no. I think, what does it say? A divisor of the total. Oh, okay. I think this problem, let's just do a slightly different problem because, it seems like, yeah. So let's do the proper divisors problem. So let's say there's only one stack, okay, one heap. Let's say I start with 30. So, do two of you guys want to play this game where you can only take a proper divisor of the current number? Okay, Alan can play. Do you want to play me, Alan, or does someone else want to play Alan? I forget how this works, so I might choose the losing strategy instead of the winning strategy because I don't remember which one is which. But okay, so do you want to go first or do you want me to go first, Alan? Wait. So when is let's see, takes the last stone? No, when is let's say force, the winning condition is force opponent to take the last stone. So force opponent to take last stone. Okay, I'll go first. I'll take away 3. So now you have to take away a proper divisor of 27. Okay. Let's see. I'll take away 1. So now you need proper divisor of 25. Oh, wait. Okay. I'll take away 3. So now it's at 21. Okay, I'll take away 5. Okay, you always take away 1. Let's see how this pans out. So yeah. Okay, so let's say Alan is a machine who always wants to take away 1. So I'll take away 7. Oh, 7 is prime, so Alan probably has to take away 1. Okay, so I'll take away 1. I'll just take away 3. Oh, 3 is prime, so Alan has to take away 1. So I'll take away 1. Uh-oh. No. So the person who has to take the last stone kind of loses. I mean, I forced the opponent to take the last stone, so I happen to remember. So 1 is technically, I guess 1 is a divisor of itself. So okay, so somehow I won because I remember this strategy after talking about it for a bit. Okay. Does anyone see how to win or lose, or force a win or force the opponent to lose? So I'll just mark where I chose something. This was like, then this was like me. Okay, so Alan says parity. Yeah, so yeah, it seems like every time it was my turn, I happened to receive an even number. But did Alan have to give me an even number after each of one of my choices? Yeah, so how did I make my, Sonak says yeah. So how did I make my choices to make Alan have to give me an even number? Yeah, so give an odd number, yeah. So I always choose an odd divisor of the current even number, which I'm always given if I start off with even. And then Alan is always forced to have an odd number. So all the proper divisors of odd numbers are odd. So he has to take away an odd, and then I'm back with an even again. That keeps going until I get like some small even number like 2. And 2 is winning because 1 is losing. Yeah. So it's like all factors of odds are odd. And all factors of even, if it's, for even, I can always take away 1. Like I could have taken away any odd factor of 30 and it would have been a winning position. So yay, we're all less dim now. And we can move on to the next problem, which doesn't mention being nim or dim. So just, this is poking fun as the game of nim, which is like what all of these games are. So technically I didn't answer this question, but this question is a bit harder than, like this is the general game of nim, I think, with, yeah, we'll have to solve this a bit later. So, but let's do number 6 first before we solve number 5 in general. So this time, instead of a proper divisor of the current number, you take away any power of 2. So how should we investigate powers of 2? Let's see. If I can scroll down properly. So this time, do 2 of you want to play a game with each other? This time I will not participate. Okay, I volunteer Sonak as well. And then someone else, it can be Alan again, but it can also be Adrita or Josiah. Okay, Adrita can do it. Here, you guys can just say it out loud if you really want to. So let's say I start off with the number, let's say I start off with 31, let's say. Yeah, place your bets. Okay, who wants to go first, or who wants the other person to go first? Okay. Okay, Alan will go first. I mean, sorry, Sonak will go first. Sorry, I forgot who was playing already. So Sonak versus Adrita. Okay, Sonak will go first. So you have to take away any power of 2 at any turn. Okay, so Sonak takes away 1.
2.
Okay.
1.
Okay.
4.
Okay.
16.
Okay.
Wait, who wins? The person who takes the last?
Let's see, what does it say again? The person who cannot move loses. So if you're at 0,
Oh.
you cannot lose. I mean, you cannot move. Sorry.
4.
Okay.
Two.
One.
Oh, okay. I guess it would have been the same either way from 3, but okay. So now it's Sonak's turn and he cannot move. So Adrita wins. Okay. So let's see. Is there some strategy we can come up with looking at this game? Yeah, Josiah, Alan, do you guys want to play a game? I think we should play one more. So I'm gonna say Josiah and Alan, if assuming they're both there. Okay. You guys, I don't care if you type it or if you want to. So here, let's just put Josiah versus Alan. Okay. So the rules are you take away any power of 2, including 2 to the 0, which is 1 on any turn for both players. And then if you're at 0, then you just lose because you can't move anymore. Okay, so I'm gonna say I start off at 57. So who wants to go first? Okay, I'm gonna choose Josiah to go first. Okay, so Joe goes 32, so that's 25. Can you think backwards 25 steps? That will be tough. Yeah, it will be very hard. It's okay. Alan is a robot with a random number generator. So he has like partial random number generation capabilities. So he's not hopeless as a robot. Okay, Josiah, Joe, you have 21. Okay, 16. Okay, Alan, you have 5. Okay, now it is possible to plan your actions carefully. Okay, Joe has 4. Wait, who wins? I'm trying to think. So you do not want to start your turn with 0. Did Joe say anything yet? Let's see. Oh, wait. Are you allowed to take the whole stack? I guess that's fine. Yeah. Okay. Yeah. I guess technically you can take the whole stack. That's fine. Okay. So it looks like Alan cannot make a move. So Alan loses. Okay. So, we can keep playing, but let's just, do what we did in the first few steps. So, okay, Joe wins. Okay, so 1, is that losing or winning? Let's work backwards. This will be my strategy to work. Maybe binary has to do with it, maybe. So if I take away 1, then the opponent loses with 0. What about 2? So if I take away 2, I can take away 2, so this is winning. What about 3? Well, no matter which power of 2 I take away, the opponent has a winning position, so this is losing. What about 4? Yeah, I can just take away 4 directly and automatically win. What about 5? Are you sure? Is there no way I can force my opponent to... Yeah, how can I win with 5? Yeah, I can take away 2, right? I can take away 2, and that forces the opponent into a losing position, from which then I can perfectly play and win. What about 6? Let's see, if I take away 1 or 2 or 4, oh, my opponent always has a winning position. So, okay, this is losing. What about 7? Yeah, maybe it's multiples of 3. Interesting observation. So yeah, I can just take away 1, and then the opponent has 6 and it's losing. What about 8? So I can take away 2, give my opponent a... What about 9? So let's see, I can take away 1, 2, 4, or 8. Looks like all of them gives my opponent winning, so it's losing. Okay, the conjecture is multiples of 3, right? Not 9, 3. So how can we prove this? So, okay, it seems like mod 3 has something to do with it, right? So if we go back to our problem statement, what's true about all the possible moves on any given turn? What are the powers of 2 in mod 3? Yeah, none are 0 mod 3. Good. So they alternate 2, 1, 2, 1. So none of them are 0 mod 3. They're always 1 or 2 mod 3. So let's say I'm at a big power of 3, right? I mean, a big multiple of 3, like 1002. Let's say we proved by induction that 999 was losing. So then, okay, if I'm it's currently my turn, right? Zinki's turn, and I have 1002. So what can I do to try to win? You know, let's see. Well, all I can do is take away powers of 2, right? Let's say I take away a power of 2 that's 1 mod 3. Now what, you guys are the opponent. What do you guys do to make me lose again? Yeah, I take away, now you guys just take away any power of 2 that's 2 mod 3. And then that puts me back at 0 mod 3 because I was at 0 mod 3 to start with. And by the inductive hypothesis, all previous multiples of 3 were losing. Like we could have, started at 0, 3, 9, 3, 6, 9. So yeah, so if you're currently at a multiple of 3, no matter what you do, you can't give the opponent a multiple of 3, right? Because all the powers of 2 are not 0 mod 3. And then if your opponent is not at 0 mod 3, because they, you were forced to give them something that's 1 or 2 mod 3, then they can just take away any power of 2 that's, makes you, like me, like 0 mod 3. So yeah. Yeah, so maybe we should write down the strategy. Winning strategy, force the opponent to start their turn with a number that is 0 mod 3. So the only time you can't do this is if you start off 0 mod 3. and then you've lost if the opponent knows what they're doing. So okay, that's pretty cool. So this is powers of 2, but the strategy turned out to be mod 3 and not binary or anything like that. Yeah, so if it's 0 mod 3, you do want to go second. If it's not 0 mod 3, you want to go first. Okay, so that's kind of an interesting problem, maybe a bit unexpected. Let's see. So those are some games with invariants. Like there's some invariance mod 3 or mod whatever. So now let's see. Yeah, math counts. Technically, this is a middle school handout, but I think it's hard enough to be considered like Olympiad level. So maybe not the math counts problem necessarily, but there is the idea of an invariant. So it's like, give it 25 years and math counts will be like pre-Olympiad level, and everything gets harder and harder. Okay. So 25, 25, 34 removed from the jar and put it in the second jar. What is the positive difference between blue in the second jar and the yellow in the first jar? Okay. So first jar, you have 25, 25, blue, yellow. And then let's just do any random move, right? I don't know what's going on yet, so I'll just do any random move. So let's say I remove 25 blue. So now this has 25. So this is second jar. And then it has 9 yellow. So maybe I should write it like this. So this is second jar. So blue, yellow. This is 25. This has 9. And now there's 0 blues in the first jar and like 16 in the second. So supposedly the answer is the same no matter how you do it. So what does it say? Difference between blue in the second jar and the yellow in the first jar. So it looks like 9. No, positive difference, not sum. So what if we had done something else? Like, let's say I removed 17 and 17, right? So I have 8 and 8 and 17 and 17 in the second jar. So this is, oh, it's still 9, right? Blue, yellow, blue, yellow. Okay, so what if, let's do a variables, So what if I removed x here and 34 minus x here? So that I'm left with 25 minus x. And so this will be 25 minus 34 minus x, or just -9 plus x. So then, I guess I'm left with x here in the blue, and let's see, 34 minus x in the yellow in the second jar. So what was it asking for? Number of blue in the first jar and yellow in this, yellow in the first jar. So it's this number and this number. Oh yeah, it is, the positive difference is 9. Okay. So it said yellow in the second jar. No. Blue in the second jar. Okay, that's fine. Yellow in the first jar. Sorry, I keep scrolling. I have really bad memory of the problem statement sometimes. Okay, so yeah, it's the difference between the two circle things is always 9. So yeah, no matter how I do it, the difference, the answer to the problem is 9. So that's an invariant of this, this situation. Okay, so we can do number 2. A circle is divided into 6 sectors. A pawn stands on each of them. So 6 sectors. You have 1 pawn on each. It is allowed to shift any 2 pawns to bordering sectors, to sectors bordering those they stand on at the moment. Is it possible to gather all pawns into 1 sector? Well, this isn't chess. This is some sort of hexagonal thing. It doesn't have to be pawns. It can be like stones or sticks or something. Or checkers. So let's see. So maybe, you know, I'll go 0, 0, 2, 2, 1, 1 by moving this over there and this over there. And then maybe I'll try moving, you know, I'll take 2 steps and move it to 1 over there and 1 over, oh, no, that doesn't work. They have to be neighboring. Oh, it is allowed to shift any 2 pawns to sectors bordering those they stand on. Oh, okay, that is allowed. So I can move that there and that there to make it 1, 2, 2, 1, 0, 0. And then I can make it, you know, 0, 0, 0, 3, 3. Uh-oh, we have some problems. Okay, Joe says, I don't think it's possible. Yeah, my pen just like, yeah, okay. Okay, so we might have, you know, maybe let's try one more time. We have some evidence to suggest that it's not possible. So let's try 3, 0, 0 like this. And then we can try 1, 1, 3, 0, 1. And then we can try like 1, 4, 1, 0. And then we can try 1, 5. Okay, it still doesn't work. Now they have to switch back and forth, kind of. If you have neighboring 3s, it's not possible, or any group of 3s? Okay. So how can we prove that it'll never work? Is there an easy way to like explain it? So let's see. You can try some more examples, but what if I color, like let's say I color some of the regions, right? I'll color every other one black. Does that help? So we start off with 1 in each sector. So what could happen on any given move, right? So, okay, there's some possibilities, right? So let's say on a given move, we could have 2 whites move to a black square, right? So at the first, we have 3 in the whites and 3 in the blacks, right? So we could decrease the whites by 2, right? And increase the numbers on the black squares by 2. What's another possibility? Well, yeah, so we could have like 1 move from black to white and another 1 move from white to black. So we have 0 total and 0 total change for the blacks, like the total number of pawns in black squares and the total number of pawns in white squares or white sectors, right? The only other possibility is +2 and -2. I could have, you know, 2 more go to whites, and you know, that would mean 2 less in the black sectors. So if we start off at 3 and 3, you know, why can't I make it 0 and 6? Yeah, now it should be clear, right? Like, what is invariant about the number of white, like pawns on white sectors? Yeah, so the parity of this number, it's always odd. I can only change it to 1 or 5 or 3, right? I can never change the parity of the total number of pawns in all the white sectors combined, because each time I move 2 pawns to an adjacent sectors, which means 2 pawns switch to the other side, so you can only have a net +2 effect or +0 effect or -2. So yeah, so you can never have, you know, 4 pawns on white squares because each move shifts 2 pawns to the opposite color. So yeah, you'll have +2, +0, or -2 for the total number in white sectors. And same for, and the opposite, you know, in black sectors, I guess. Okay. So that's interesting. So let's look at number 3. I should give you guys a bit more time to try it on your own too. So these are trees, but I'm too lazy to draw a tree. So we'll just pretend all of these are trees. So there's 1 on each tree. And then on each move, like you can have 1 owl fly 2 that way. And then some other owl flies the same distance the other direction. So you could go from there to like 1, 0, 2, 2, 0, 1, for instance. So can they all gather on one tree? So Alan guesses only odds, not a bad guess. What happens if it's even? Like, okay, with 2, it's obvious. With 2 trees, then they can never gather because they'll just keep switching places with each other. What about with 4? Can they all gather at the same tree if there's 4 trees and 1 to start with at each of them? So we could do that and that, 0, 0, 2, 2. Oh, that's probably not helpful. We can move those 2, 2, 0, 0 after 2 moves. Yeah, they would keep switching in the middle. For evens, it does that. Yeah. So, you know, how could we kind of like explain it a bit more clearly other than the middle 2 keep switching with each other? Yeah. So Drita says it works when it's odd. Yeah. So, you know, what is the strategy with 7 trees? So, you know, I guess it's pretty clear. We should go to the middle one, right? So there, and then there. and then there. So that's pretty easy. So with odds, you can always do something like that, and they'll always work. So the sum, Sonak says the sum of net travel is always 0, but the net travel has to be 1 or -1 with an even number of trees. I see what you're saying, I think. So there's another labeling we can do. Like last time we labeled them black and white. This time, like, is there some way I can label the trees? Yeah. So let's say I label the trees 1, 2, 3, 4, 5, 6, right? So each tree has a weight. The weight is 1 through 6. 1, 2, 3, 4, 5, or 6. There's one owl in each tree. So what happens when two owls, like, you know, when one owl moves that way and the other owl moves this way, what happens? What happens to like the sum of all the weights or something? So now there's 0, 2, 0, 2, 0, 1. Oh wait, sorry, this is 1. Yeah, it doesn't change. It's invariant. The sum doesn't change. So originally, the sum of all the tree numbers weights was 21, right? There's 1 on each of these trees. After any number of moves, the sum is always 21. Yeah, so we need the sum over the number to be an integer. So, okay, so if we have an even number, let's see. Oh, wait. Okay, so let's say we have an even number, right? So the number is 2n, and the sum of all the integers from 1 to n is like 2n times 2n plus, so this is our total number of trees. And this is our sum, right? n 2n plus 1. So if I divide this by the total number of trees, is it an integer? Yeah, it looks like no, right? Like 21 over 6, that's not an integer. It's halfway between two integers. So this is an odd number plus divided by 2, which is never an integer. So, the same thing happens if we have 8 trees. 8 times 9 over 2, that's the sum of all the weights. And you divide it by 8, that's 36 over 8, it's not an integer. So you just label the trees 1 through 8, and the sum is always, 36. Because if I add 3 to one owl's weight, tree weight, another owl loses 3 in terms of like the weight of the tree they're standing on. So yeah, so it never works for whatchamacallit, for even numbers, and odd numbers it clearly works where they just go to the middle. Okay, yeah, so we do need n plus n. We need this to be this divided by n to be an integer, so this part needs to be an integer. So yeah, n should be odd. Okay. So let's just take a 5-minute break. You guys can look at the problems if you want, but I'm gonna take a break from talking. So we can resume. I was wondering if on the last problem, like, what if we labeled it 0, 1, 0, 1, 0, 1? Like black, white, black, white, black, white, or something. So there's 6 trees. I'll just say these are trees. So if I go 3 and 3, you know, it, yeah, so maybe we could have labeled the trees as like a black tree and a white tree, black and a white, black and a white tree, and there's 1 in each of them, right? And then after any number of moves, there's always going to be, you know, plus, you know, there's 3 blacks in the total and 3 whites to start with. So you can never have 6 all in one, because each time you either increase the number of whites by 2 or increase the number of black trees by 2, or like they're opposite parity and they stay the same. So we could have done it with 0, 1, 0, 1, 0, 1 as well. We didn't have to go 0, I mean 1, 2, 3, 4, 5, 6. Okay, so that's kind of an interesting thing to note. Okay. So let's try the camel one. Sure, just paste it here. But it's not a knight. It goes 1 and 3, not 1 and 2. Yeah, it's a long hopper or a grasshopper, or I think a grasshopper would be an okay name, but camel is fine as well. Anthony. Yeah, so all of the invariant questions we've been doing, they've all been kind of no so far. But, you know, how can we prove that, you know, can we move to an adjacent square here or not? Yeah, a regular knight can, like, you know, a knight could go here, here, there. That's fine. But why can't the camel do that? Or can it? So 1, 3. So, you know, if I have some infinite grid, why can't the camel do it? So, you know, 1, 3, 1, 3, 1, 3, 1, 3. Oh, wait. Yeah, I think I messed something up. Yeah, what's true about all these like squares that it could have ended up on? Yeah, so let's see. Yeah, so we can checkerboard color it. So what happens if I checkerboard color it? I'll just make it red instead of black. So what does a camel do when you move it on checkerboard? Can it ever go from white to red? Yeah, you always end up on the same color. It can't ever go to an opposite color. So because all 4 adjacent squares are the opposite color, you can never go to an adjacent square. Like all of these are elite. You'll never go to an adjacent square. Okay. Let's look at number 5. So the topic is invariance. Okay. So I can add 1 to numbers in adjacent sectors. So can I make them all equal? If so, why? I mean, how? If not, why not? Okay, so parity or checker it. Okay, yeah, so what happens if you checker it? So I start off with 1, 1, 0, 0, 0, 0. What does each move do? So each move, it says you add 1 to adjacent sectors, right? So it says adjacent. So I can add 1 to here, like +1, +1. I can add 1 to there, +1, +1. So what happens? What stays invariant each time I add 1 to adjacent sectors? Okay, so the positive difference in the sums of the black and white squares is the same. Yeah, so each time I'll add 1 to a black square number or a 1 to a white square number, right? Or a sector number. So at the start, the blacks, they had 2, right? 2 total in black sectors and 0 in whites. Each time I add 1 to the total number in the black sectors and white sectors, so the difference is always 2 and it can never be 0. Yeah, so it's not possible for all 6 sectors to have the same number, right? Okay, so that seems good. Uh, So do we suspect the same number will be on the board each time? No matter how you do it? Yeah, so there will always only be one number after 19 operations. Yeah, so Alan says the net sum decreases by 1 on each move. So what's the net sum after before any moves? Is it 190? So it's like 20 times 21 over 2 or 210, is that right? Okay. So then, yeah, what happens after 19 moves? What's the sum of all the numbers on the board after 19 moves? It's okay. I often fail at quick math as well. So yeah, we'll just have the sum will just be 19 less, right? So I think it's 191. I don't know. I think there might be a typo in the handout on some of this. So yeah, I think it's 191. Oh, wait, after 19 moves. Yeah, 191. Yeah. Okay. So yeah, the invariant is that the sum of all the numbers on the board plus the number of moves that has happened is an invariant. So you could say the net sum is a monovariant where it decreases by 1 each time. So mono means like in one direction. Monovariant is just something that always increases or always decreases. An invariant is something that never changes. Okay. We'll try 7. Yeah, what's after this? Is it just, okay, that's fine. May erase 2 numbers on the blackboard, but you must write the positive difference. Oh, I see. So I emailed everyone the handout, I think. It's intro CP, it's this one. Okay, so Adrita says the sum and the difference have the same parity. Yeah, that's true. Right. That's exactly the right idea. So, if I take, let's say, yeah, we should look at parity. If I pick 2 odd numbers to start with, their sum is even and their difference is even, right? So the sum has the same parity as the difference. If I picked an odd and an even, then both the sum and the difference is odd, right? The sum is odd and the difference is odd. If I picked even odd, odd even, that's the same. If I pick 2 evens, the sum is even and the difference is even, right? So sum, difference. So yeah, so I can, so yeah, the original sum, like, yeah, like I think Sonak said was this number, which is odd, right? This is odd times odd. So at each step, the difference, like, yeah, at each step, the sum will be an odd number, I guess. Because like if I replace two odds with, I replace two odds with an even number. That's the same as like adding the two odds and getting an even number. So the parity, will never change. So because we solve with an odd parity sum, then the sum of all the numbers on the board will be odd at each step. Because when I replace two numbers, their sum is deleted and their sum has the same, parity as their difference. So it won't change the sum of all the remaining n-1 numbers. Okay, cool. POP is power of parity. Yeah, I mean, yeah, it seems like this handout seems to show that parity is a very useful thing to consider. Oh no, number 8. I don't know if we can solve this. Let's see. Let's see. Oh, okay. Oh, huh. So let's try with the 4x4 first. So 0 mean white, and let's just make it ones and zeros. So either I can repaint, I can toggle whether it's 0 or 1 in a 2x2, or I can toggle whether it's 0 or 1 in a column or in a row. So can I ever make just one square, the only one of its color? Let's see. So yeah, it seems like parity has something to do with it. So let's say I toggle everything in the first column. So now it's 1, 0, 1, 0, and then 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. So that's if I toggle the first column, the red column. Now what can I do? Can I change the total number of ones? Oh, so now, I see one vote for possibly yes. The answer is yes. I don't know. I haven't done this problem, I don't think. It's been a very long time since I've done it, so I can't remember. So how can we get yes? Let's see. Can we? Maybe we can. 32 black to 1 black, which means 3, 2 black to 1 black. So let's try it. It looks like I can change like let's say I do this one, so it becomes 0, 0, 1, 0. Now what? Remove all 2x2 squares except for. No. So like when it says repaint, it means like change to the opposite color, I think. Yeah, I think that's what it means by repaint. Okay, so Joe says 1, 1, 0. Let's do the middle column. I mean the third column. So 1, 1, 1, 1, and then 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0. So now what? Toggling 4 at a time cannot change black square number parity. Yeah, I think that's right. So now, yeah, so if it starts even, it can't be odd. Let's see, is that always true? Yeah, so even if we did this, this would change the number of ones from 1 to 3. So it increases by 2, or it increases by 0, or it increases by -2 each time. Or it increases by 4 each time. So yeah, toggling, repainting everything the opposite color will always, like the number of blacks will always be +2, +4, +0, -2, or -4. So yeah, we can never read an odd number. Yeah, so 1 isn't even. So yeah, 0 can be black, it doesn't really matter, or 0 can be white. So either we have 0 equals black and 1 equals white, or vice versa. It doesn't really matter which way. Like 31 black or like 63 black is the same as like 1 black if we just switch all the colors. So yeah, it looks like it's still not possible. I wish the chat could stay up. Okay. Why won't the chat stay up? Okay. Oh, this is not really related to invariance. Maybe we can just read through it, but I don't think this is really related. Let's see. Let's see. Yeah, I think maybe we can save this for another day. Let's see, what should... Okay, I'll just, I was gonna do this with another class, but I guess I'll just do it here first. So let's say we have the set 1, 2, 3, 4, 5, 6, 7, 8, 9. Game. 2 players take turns taking 1 number away from the set. So the player who reaches a sum of like, let's see, yeah. The player who reaches a sum of 3. So if you ever have 3 numbers that add up to 15, then you win. So it could be that you have 4 or 5 numbers, but if any 3 of them make a sum of 15, then you'll win. So it's like people take turns taking 1 away, right? So person A and person B, they can take away 1 at a time. And obviously this is not the best choice, but this could be a possible game that they play, where first move, second move, third move, fourth move, fifth move, sixth move, seventh move, eighth move, ninth move, or something like that. So the first person to get like 3 numbers that add up to 15 wins. yeah, so it's possible that neither gets to 15. Wait, so is my example, is it a draw in my example? Let me see. No, my example has a winner because like this makes 15, right? So A would win on the fifth move. Does someone win before the fifth move? Or if A's fifth move? I don't think so. Oh, no. This is a win, right? 9, 4, 6. So B would win on his fourth move. Actually, maybe draws are possible, but maybe they're not possible with best play. But I'll let you think about it. Yeah, so you can't pick a number twice. So all 9 numbers are distinct. They're just the numbers 1 through 9. So yeah, the question is like, who wins with optimal play? Player 1 or 2? Or is it always a draw with optimal play? This has nothing to do with invariance, by the way. It's just something, that is pretty cool. So if so, what is the winning strat? So I'll let you guys think about it. If you guys want to play, I mean, it's kind of hard to, yeah, I'll let you think about it for a while. Okay, so Alan says maybe the first optimal pick is 5. That makes sense since like 5, like 5 kind of has the most, like, 5 could be 1, 9, 2, 2, 8, 3, 7, 4, 6. There's like 4 sets with 5 and maybe fewer with the others. So it makes sense to pick 5 first. So here, let's talk about something else that we'll come back to. Do you guys know who wins in tic-tac-toe with optimal play? Or is it always a draw? Yeah, it's always a draw. Like, let's say person 1 goes here. Then I guess, person 2 could go here. I mean, yeah, if you just try out all the possibilities, like let's say, there's 3 possible first moves. I think if you go here and then person 2 goes here and then you just go here, then do you always win? Let's see, if I go, I know if 2 goes here, then 1 would win because then they have 2 winning positions. But yeah, so maybe you can relate it to, can we relate this to tic-tac-toe in any way? In tic-tac-toe, the best move is the center square for the first player. And then the second player, they can do like, I think if they do this, then maybe the first player can win. Because then, you know, 1, and then there's 2 winning positions for number 1. But if 2 goes into a corner, then they can't win. You can just try all the possibilities. Yeah, I mean, there's only so many possibilities to try. So if you play a lot on your own, then yeah. So how can I relate? This is pretty hard, but how can I relate this game to tic-tac-toe? Okay. So here's a question. Do you guys know how to make a magic square if you have an odd number of sides? Or if n is odd? So to make a magic square, what you do is you put 1 in the top middle, and then you go there and you put the next number. So this number, it's like this number. It's like when you go off the right of the world, you come back on the left of the world. If you go up the top of the world, you come back on the bottom of the world. You go there to 3. If the next number is blocked, you put the next number below it. So 4, and then 5, and then 6. The next number is 4, that's blocked. So you go down 6, 7, and then you go to 8, and then you go 9. This also works for like, so all the diagonals sum to 15, the 2 longest diagonals sum to 15, and all the each row and each column sums to 15. So yeah, what's the connection here? You know, like what happens if I just put these 9 numbers on the whatchamacallit, a magic square? Yeah, so this is isomorphic. It's the same shape and the same structure as tic-tac-toe. So we can just put the 9 numbers in the arrangement like I just said. 1, 2, 3, 4, 5, 6, 7, 8, 9. And with optimal play, you can never win. It'll always be a draw in tic-tac-toe. So the original problem is also always a draw with optimal play. You always pick 5 first, and then it becomes a tic-tac-toe game on this board. So that's interesting because you can always block, you know, what the other person's doing. Okay. So I thought this was like really, really cool when I first saw it. It's like, wow, this game is like the same as tic-tac-toe if you put the numbers in the 3x3 grid the right way. This is amazing. Yeah, this is like, you know, you wouldn't think it's the same structure as tic-tac-toe, but this labeling of the 3x3 grid makes it the exact same game as tic-tac-toe. So, you know, what I was saying earlier is this also works for like n by n grid when n is odd to make the magic square, unrelated to the first game. So if you have a 5x5, you can make a magic square just by, you know, doing the same thing. So 3, oops, let's do it in green. 3, 4, 5, 6. Now you have to go down 1, 7, 8, 9, 10. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So yeah, you always go to the, always go this way. If this square is blocked, then you go down. You always go northeast or south. First, try northeast. If the square there is blocked, then you go south 1 square. So that's how you can make a tic-tac-toe. Yeah. I mean, that's how you can make a magic square with an odd number of side lengths. Yeah, but tic-tac-toe, it's like super well known to be a draw. Like most combinatorial game theorists, like it's like pretty well known. Like I mean, there's only so many cases to try. Like the first move, there's only 3 possible first moves. You do a center square, an edge square, or a corner square. And then, there's only so many cases to try. Sometimes you win on the third move, like your third move. So yeah, it's definitely doable to check out the cases. And I think it's well known enough that tic-tac-toe is a draw. That, yeah. I mean, I don't know about Jane. It seems very unlikely that this would appear on an Olympiad, but at least on the USA Olympiad, maybe in Russia or like some Balkan country on like a middle school Olympiad, maybe. But I kind of doubt that this will be like Olympiad problem in the US, because it's just, I mean, this kind of problem, it's not the best Olympiad problem because it's like there's like a really clever strategy, which if you don't think of it, which like it's very hard to think of, you just kind of won't get it. I mean, no, you can still solve it without it, but like I don't know. I feel like this solution is almost like cheating if you're like trying to brute force the original problem without this insight. It's so amazing. It's like cheating. Yeah. But some, I guess some whatchamacallit, like in Russia and in like some Eastern European countries, they have like junior Olympiads for like middle school students. And maybe I don't know, it feels more of that kind of flavor of problem. Okay. So okay. I don't have anything else planned for today, but I saw, let's see, Sonak had asked a question about like one of the problems from one of the classes. So maybe we can look at it. Because I haven't thought about this in a long time. So I don't know if I've ever solved it. So maybe we can solve it together. Since this is office hours, this is kind of fine. This looks really hard. Is it even true? Oh, okay. I see it now. So I think I see. Like, can you even find another example other than p equals 3? I tried some small primes for p, but all of them made p squared plus 1 composite. No, if p is 5, then p squared, this is 27, which is not prime. You need both of these to be prime. So if we try 7, that's not prime. If we try 11, that's not prime. If we try 13, that's not prime. Yeah, what's true about all of these examples? Like, why isn't this prime? Yeah, they're divisible by 3. Is that always the case? Yeah, so we should look at it mod 3. So, for primes that are bigger than 3, it's always 1 or 2 mod 3, right? So if we square 1 mod 3 and add 2 to it, it's 0 mod 3. If I square 2 mod 3 and something that's 2 mod 3 and add 2 to it, it's 0 mod 3. So if this is not 3, then this is never prime. So there's only one example to this, which is when p equals 3, in which case this happens to be prime. So yeah, I guess it was not, it was much easier than I was thinking for some reason. Okay. Yeah, so it doesn't look like one of those problems with limited solutions, but apparently it is. Okay. Do you want to share it, Sona? That's fine. I mean, I have yeah. I mean, I can choose some problems from problem solving strategies, but I'd rather not. Yeah, you can just type your problem. That's fine. I'll just copy it into the PDF annotator. But in the meantime, is there any other cool thing that I can share that's math related? Let's see. Yeah, so the link I'm looking at for problem solving strategies is it's this link. Actually, there's probably like a PDF that I have saved somewhere. But there's the first chapter is on invariance, and that's what we talked about today. But I want to take a look at yeah. So let me just copy this problem and we can take a look at it. Oh, okay. I see. Does anyone else see? Wait, is it? Oh, okay. That's fine. But that's still I think I see what's invariant. Oh wait, no, I don't see what's invariant. Hang on. Oh, I think I see. I think I've seen this before. The sum and difference have to have the same parity. Wait, the sum and difference have to have the same parity. Okay. Is that so? Okay, so let's try it with 5, 3 to 6, 2. I think I see what's in a monovariant. Is there something that's always increasing here? There is something that's always increasing. There's a quantity that's always increasing. is the sum always increasing? So let's see, 8, 2, 10, 6, 16, 4, 20, 12, maybe. But if you start off with the first number smaller than the second number, it's always maybe, I don't think that's still true. Yeah. So I think the key idea here is, you know, the number in the first parameter is increasing. What if we started off with like 3, 5 though? So this would be 8, negative 2. Maybe if you start off with negative numbers, then it's like different. So negative 2, negative 4, negative 6, positive 2, negative 4, 8. I mean, negative 8. I don't know. But yeah, I see a monovariant. So yeah, so we need like something like this and they're positive for the condition that A is increasing to be true. But yeah, I think I see, okay. So now we change it. So you're saying AB goes to 0.6A plus 0.8B and 0.6A minus 0.8B. Okay. I think it should be, maybe let's make it 0.8B minus 0.6A. I think that would make, I think it would be better like this. Maybe this is better. The thing you wrote originally, Sonat, the A is like, yeah, you have 0.6A in both of them. I'm not sure if that works. Like if it was actually 0.6A in both, I don't think it would work. And it doesn't matter which is which really, because you can always switch to two numbers. So there's one thing that's invariant. Like in the original problem, let's see. I think what's invariant is that like if I take the sum of the squares, like A squared plus B squared, here the sum of the squares is this squared plus this squared, which is 2A squared plus 2B squared. So the sum of the squares always doubles. So here you can't go from like 41 to 40. But in this example, the sum of the squares, what happens to it? So let's see, 0.36A squared plus 0.64A squared, that's just A squared. And then the 0.64B squared plus negative, so 0.36B squared is always B squared. So this is invariant. So the quantity A squared plus B squared for each pair, it never changes. So yeah, that would be an invariant for that problem. Yeah. So here it's increasing, monovariant, and there it's, invariant. Okay, so let's do a quick algebra geometry kind of thing. Like, let's say A, B, C are the sides of a triangle, and I want to express AB, BC, and we'll talk about it in a future class too. So we want to express this in terms of the semi-perimeter, the circumradius, and the in radius. So I don't know if we have enough time to do it right now. So the key idea here is one formula that might be useful is like a plus b plus c is 2 times the semi-perimeter, right? Another formula that's useful is this is true. So this is 4 times like the semi-perimeter times radius times this. So there's these two formulas. We might wonder if there's a formula for the sum taken 2 at a time. Yeah, so let's do Vietas. So let's say we have a root, like these are the roots of some polynomial, right? So how can I relate this to S, and how can I relate it to like area?
You have
Okay.
yeah.
I see what you typed, Adrita, and that is true. Oh no, it's 1/2 of the right-hand side you typed. But that is true. So what if I plugged in S, like let's say this is P of X, right? What's P of S? Is this related to something we might know? So I plugged in the semi-perimeter into the polynomial. Yeah, so let's actually define, the polynomial to be like this. So, like, I guess I just plug in the semi-perimeter into this polynomial, and I get the area of the triangle square, right? So this is k squared. So k is the area of our triangle. But then this is just, s times s cubed minus the sum of the variables, s squared, plus the sum taken 2 at a time, s, minus abc, right? So this is r squared s squared. So we can just, we can cancel out one s. And now we can solve for this part. So we just get s cubed minus, so technically this is like, yeah, this is okay. The sum of the 3 sides plus the thing we're looking for minus ABC is r squared s. So then we just rearrange. So, we'll just get like r squared s plus ABC minus s cubed equals plus sum a s squared equals sum ab s. So these are all cyclic sums over a, b, and c. So now we can use all the formulas we know. Like this is, ABC was 4 times the area times the whatever. This is just s cubed. This is just 2s for the sum of the 3 sides of the triangle. And this equals sum AB of s. So now we can just like, this is like r squared. We can plug in rs for this. And we can plug in this, and we can plug in, so this is squared, so plus 2s cubed. So then we can divide everything by s, and we get this. So this is equal to, r squared plus 4rr plus s squared. So this is s squared plus r squared plus 4rr. So let's check. Maybe I made a mistake, right? So let's just double check. Let's say we have an equilateral triangle. Let's say the side length is like 2. No, let's make it like 6. So then this is 2 root 3. The in radius is root 3, and half the side length is 3. So S would be 9, little r would be root 3, and capital R would be 2 root 3. So is this true? Let's see. So 108 equals 81 plus 3 plus 27. No, what is that? 12 times, so 30, 12 times 4. No, sorry. So this is 6, so 4 times 6. Yeah, that's true. So, okay, we don't have like a mistake somewhere that we can detect so far. So it looks reasonable, right? Like we plug in some numbers with an equilateral triangle seem to work out okay. So I didn't like change a positive sign to a negative sign or something, some silly mistake like that we can detect. So maybe it's okay. So, this is useful when you want to like length bash some geometry problem. Like it turns out you can always get the symmetric polynomials in terms of like S, R, and R. You can always get, this, and this. Like any combination of this stuff you can get in terms of the semi-perimeter, the circumradius, and the in-radius, and vice versa. So that's kind of interesting. So yeah, it can help you solve some problems, but we'll talk about it in a later class.